My name is Wilckyster Nyateko, Ogutu, and my supervisors are Dr. Min Mugera, Professor Tekalti, and an external supervisor, Gideon Obare. So this is part of my research work, one of my objectives that I'll be presenting today. So I'm working on adoption of sustainable agricultural intensification practices in Kenya. And this is an analysis of choices among packages which are generated using K-mode clustering. So just to take you a bit on the background, first of all, I'd like to acknowledge my supervisors and the Australian Award Scholarship, which funded my education, and also the Adoption Pathways Project, which collected the data, and it is part of CIMIT. So just to take you through a little bit of an introduction, enhancing smallholder agriculture is very key in increasing productivity. This is especially in Africa, where small-scale farmers where farmers are predominantly small scale and who depend on agriculture for food and income. And the report by FAO and World Bank has shown continual evidence in low productivity. And then, therefore, transforming smallholder agriculture will require transformation from the subsistence agriculture to one that is innovative, more of commercially oriented, and modern. So there are several challenges facing the agricultural sector in developing countries. One of them is dependence on rain-fed agriculture. We also have declined soil fertility, continuous land subdivision, and this is as a result of rapid population growth. We have severe droughts and floods, which are frequent due to climate change, and high cost of domestic food production. High cost of domestic food production as a result of high input cost, especially fertilizer, and also institutional and political failures. So the current report by FAO, that is just, by 2017, shows, as you can see, the population growth rate. In Europe, North America, and Latin America, it's more or less stagnating. And if you can look at the Asia and Africa, it's increasing. But on the recent part, Asia is somehow becoming stagnant, but Africa is continuously increasing. So this implies that not unless there are changes in production system, Africa will basically remain a net purchaser. So what are some of the possible solutions that have been put in place? So initially, there was promotion of intensification, and this was during the Green Revolution. But this did not take place in Africa because of poor policy, lack of water that could be used for irrigation, and capacity to implement was very low. Second to that, the low levels of external input in these countries also could not remedy the widespread soil degradation that was already existent. And intensification alone, therefore, would not be ideal for the already degraded land. Later on, there was a promotion of conservation agriculture, which was proposed to be an environmentally friendly approach to improve productivity. And the basic three components of conservation agriculture include minimum tillage, or what most studies refer to as direct seeding, soil cover or mulch, and crop rotation. But after the promotion of seahead, this has not also helped in alleviating the food shortage because of the slow release of nutrients, especially the green and compost manure. So sustainable agricultural intensification practices, I would be referring to this as SAI for this case, has been proposed as a win-win strategy to help in increasing the productivity, at the same time conserving the natural resource base. So the main definition that we adopted for this study is by the Royal Society in 2009. That defines this as producing more output from the same area of land with less impact on the environment while ensuring a sustainable resource base on which agriculture depends on. So for my study, or for this study, we considered 10 site practices, under which we broadly categorize as soil restoring practices and others as external inputs. Under the soil restoring practices, we have minimum tillage, soil and water conservation practices, which are short-term, the long-term soil and water conservation practices, maize and legume intercrop, rotation, and organic manure. And under the external inputs, which are basically commercial inputs, we use improved variety, pesticides, herbicides, and fertilizer. So we adopt a conceptual framework by the Montepella 2013 in directing our studies. And under this, we have, in production, we have inputs divided as in two categories, as direct inputs and indirect inputs. The direct inputs include labor, water, inorganic chemicals, and so on. And some of the direct inputs include financial capital, knowledge, infrastructure. Then we have the intensification process. Under the intensification process, there are three broad categories: ecological intensification. These include practices such as minimum tillage, rotation, conservation. The genetic intensification. Under this, we have improved seed variety, pesticides, and herbicides. And then we also have the social economic intensification aspect, which is basically the social capital, such as improving the marketing channels. So when we have the intensification in place, this will result into increased production, income, as well as nutrition. And when the level of production, income, and nutrition is high, we will therefore have a sustainable environment, which is measured in terms of producing the higher amount of output with the same or less land and water, prudent use and efficient use of inputs, minimizing greenhouse gas emissions, increased natural capital resource base, and strengthen resilience, as well as reducing environmental impact. So looking at the literature that is there in place, we've seen most studies that have adopted, have focused, most studies on adoption of site practices focus on singular adoption, but very few of them focus on a combination of adoption of such technologies. There is also lack of context-specific adoption in terms of socio-economic, agroecological, and cropping systems. And we don't have studies that have looked on adoption and accounted for heterogeneity at household level, which do exist. And then we don't, there are no studies that have evaluated the determinants of various packages, especially accounting for as many as 10 site practices. Most of the studies the few studies that are there always evaluate a combination of 2 or 3 packages, 2 or 3 practices. And then the studies that are most studies that we have also are based on cross-sectional data, and no study has used the K-mode to cluster the sustainable agricultural intensification practices into groups. So the research problem is that basically empirical studies have investigated the drivers of SAI adoption. However, most of these are based or are focused on adoption of isolated practices, whereas farmers often adopt these practices as packages and in different contexts. So the objective is to identify clusters or other packages of site practices that farmers tend to adopt, to investigate the farmer preferences of the side packages based on region and cropping system, and to determine the impact of adoption on the clusters on yield. We use Kenya as our case of study, and like most sub-Saharan countries, Kenya is an agrarian economy where the rural population depend on small-scale agriculture for food and income, and maize and maize meals are the most important items in their household food basket, both in the rural and urban area as well as across all income groups. So currently there is also an increased investment in livestock sector, which also raises the demand of manufacturing animal feeds because maize is used in that sector for manufacturing the animal feeds. So, and smallholders intercrop maize and beans so as to maximize the utilization of their labor, land, so as to realize higher yield. So this therefore means that availability of maize and beans basically define the food security status. So we use a panel data from Adoption Pathway Project, which is the CIMIT-led, as I had mentioned earlier, and a multi-stage sampling technique was employed. So this is the map of Kenya. Unfortunately, I didn't put it in Africa. I mean, show the Africa map, but our study area is in two areas, regions. We have the eastern region, which is the high altitude region, and the western region, which is the low altitude region. And these regions were purposely selected, basically because they are the maize-legume production regions in Kenya, and secondly, because of the ecological zones. The two regions have bimodal rainfall pattern, and they also have two cropping seasons in a year. And proportionate random sampling was then employed in the in the district divisions up to the household level to select the households. So the first wave was in 2011, and 670 households were interviewed. And then in 2013, there was an attrition. 535 households were interviewed. And then in the last wave, which was 2015, we had 495 households being interviewed. Out of this, after removing plots that were not of maize and legumes, we are left with 3,837 plots on which we base our analysis. Basically, for the unbalanced panel data, and these are only plots with maize and legumes. So this is a framework for the methodology in the study. First of all, we have 10 sustainable agricultural practices, and then we use K-mode clustering to cluster or to package the 10 practices into different clusters, into different 5 clusters. So the various 5 clusters have got several practices, and then we use random effect multinomial logit with general structural equation modeling to evaluate the determinants of various factors for the various clusters. And then we also show the yield distribution for the various clusters. And the part which is in orange is not presented in my presentation today, but later on I would extend this to look at the impact on the various clusters on yield and income, and I would use the multinomial endogenous treatment effect to look at that. So basically, the K-mode clustering has been known to be efficient and effective for clustering of categorical data, and it uses the frequency-based to update the modes of clustering. And this uses the dissimilarity measure to define the total mismatches of the corresponding attributes of each categories, and in this case, that is the plot. So when the mismatches are small, it means that the clusters or the plots are more similar, and when they are wide, it means that they are not similar. So this is the equation representing the K-mode. So U is the partition matrix, Z is the mode of vectors, and this is the dissimilarity measure. And in K-mode analysis, the dissimilarity measure used is the simple matching distance. So when the distance is closer to 0 or 0, it means the clusters, or for this case, in this case, the clusters are more similar. And when it is closer to 1, it means that they are not similar. So for the random effect multinomial logit, this is the general form of the multinomial logit. So the difference here with the other multinomial logit is the introduction of this term, which is the latent variable, and it is introduced in the equation as a random intercept, so as to account for the heterogeneity at household level. So the second equation is the conditional probability of adoption of a given cluster. And because the mu is unknown, we therefore represent the integral, the unconditional probability, which is in the third equation, which is simply the integral of the second equation. So I'll take you through the results that we have. So this is a summary of the results that we obtained from the K-mode clustering. And basically, the values the values on the table are the mean of the specific size that are adopted by specific clusters. So for instance, in cluster 1, which we define as the yield enhancing cluster, as you can see, the colors that are in blue, we consider a proportion of which is greater than 17% of the total adoption rate to define a given cluster. So it therefore means that although we define cluster 1 as yield enhancing, it means that very few plots are having the intercrop, crop rotation, minimum tillage, and manure. The first 4 practices. So we only consider a proportion which is greater than 17%. So as you can see from the table, cluster 1, which we define as yield enhancing, has only soil and water conservation practices, improved seed, herbicide, and pesticide. Cluster 2, yeah?
The herbicide one?
Yes.
0.1?
Yes.
Should that be, am I expecting to see that to be bigger than 17%?
Oh, maybe just let me explain this. The figures in the table are the mean adoption rate. But the proportion that I consider, as you can see here, we have a mean adoption rate of 0.8%, isn't it? This is the total mean adoption rate for all the plots. But here, I consider the proportion of adoption rate per plot, per cluster.
So the reason that H is highlighted is because it's bigger than the average adoption rate.
The average adoption rate.
So it's got a 0.1, and that looks, my first thought was that's small, but now you're telling me, well, actually, no, that's big, because the average adoption rate is only 0.08. So that group is above average. Is that the way I should be looking at that number?
No, not really. We consider this as a proportion of the total. For instance, when we sum up these 0.1, 0.12, 0.06, 0.14, and 0.08, the sum of that represents 100%. So therefore, a proportion, this is only a proportion of the sum within a given practice. Is it clear? For instance, let me use another example of manure. The mean adoption rate of manure, this is a mean adoption rate not from K-mode, the figure below here. This is the mean adoption rate of manure for all plots generally. But these figures are generated from K-mode clustering to mean that under manure, the highest proportion of manure is in cluster 2. So most plots with manure are clustered in the second cluster.
So I should be comparing the numbers in the table with
Yes.
the mean, and they're going to be highlighted if the number in the table is
larger than a proportion of this. Not really this. As you can see, the mean adoption of here is, yeah. So I only consider the proportion of that for a specific cluster. I hope that is clearer. Yeah.
So is that saying that 47% of the farmers' plots in the yield enhancing cluster adopt N, which is manure?
Yes. Pardon?
Yeah, that's the, is that the correct interpretation? 47% adopt manure.
Adopted manure. It is a proportion, because if you say that, you see this is like 93%, this is 75%. So the figures here are, it's like the attributes that are generated from the K-mode clustering to allocate.
So the yield enhancing group can adopt more than one strategy?
Yes. All clusters can adopt more than one strategy. But we only consider the strategies that are dominant in a given cluster.
So yield enhancing group, 87, nearly 90% of them are adopting seed, improved seed.
I would use the proportion, not really 90% of them. Because, you know, the improved seed is, it's like 90% of them are adopted here, and that is the same, apart from the traditional. As you can see, the reason why this is traditional, it doesn't adopt, the proportion of percentage adoption in improved seed is very low at this level. So we only consider the proportion relative to the mean adoption rate. So that is how we define the cluster. So we came up with 5 clusters. The first one is yield enhancing. The second one is a cluster which adopts relatively more of the practices, yield enhancing, protecting, which is herbicide and pesticide. They also do traditional and modern seed soil restoring strategies. And then the third cluster, which is yield enhancing and traditional soil restoring. The fourth cluster basically does a number of yield enhancing, protecting, and the traditional. And then the last cluster only do the soil restoring strategy. So those are the 5 basic clusters that we came up with. So just to take you through the proportion of adoption by region from our results, we find that in the eastern region, they tend to adopt more of cluster 1 and cluster 4. And this is also, the western region adopts cluster 3 and cluster 5. And cluster 2 is relatively the same. Of course, it is higher in the western region, but at least quite a number of people also adopt it in the eastern region. So looking at adoption by year, this is also very different. If you look at cluster 2, which is the most comprehensive cluster, if I can call it that way, adoption in 2011 was very low, and this increased significantly in 2013, and also in 2015. And then we can also see that cluster 1, which is the yield enhancing, is most farmers are disadopting cluster 1. As you can see from 2011, 2013, and 2015. Yeah?
The unit of measure here is plots.
Yes.
Not farms.
No, plots.
So it's plots.
The data is at plot level, yeah. So it is the number of plots, yeah. And then we also have the proportion of adoption by crop. If we look at, we integrate the intercrop plots, bean monocrop plots and maize crop, we also see some difference in adoption. For the intercrop plots, we have cluster 3, which is the highly adopted. And then for the monocrop plots, if you take the bean monocrop plots and the maize monocrop plots, they basically adopt cluster 1, which is yield enhancing, and cluster 3. So if you look at the distribution of yield for the various clusters, so for the maize monocrop, I only considered cluster 1 and cluster 4 because monocrop plots were mostly dominant in cluster 1 and 4. And then also include cluster 5, which we use as our reference cluster. So as we can see, the traditional soil restoring, which is cluster 5, produces the least yield if we compare it with cluster 1 and cluster 4. So under maize monocrop, it means that cluster 4, which has components which are basically a combination of cluster 1 and 5, and also protecting, produces higher yields. And the same pattern is also replicated in maize monocrop. We see lower yields in cluster 5 as compared to cluster 1 and 4. And in the same also we have cluster 4, which relatively gives higher yield. So if we look at, we further segregated this into intercrop plots. So for the intercrop plots, the same cluster, the traditional soil restoring cluster also yields the least. But in cluster under intercrop, we consider cluster 2 and 3 because these are the clusters where intercrops were mainly practiced. So the same pattern is replicated also under bean intercrop. One thing to note that the maize and bean intercrop share the same area of land. So there is the results of, I maybe give some highlight on the results of the random effect logit model. So as we've seen on the results that time, region, and cropping systems are very key in adoption of SAI, as they are significant in all clusters. We also have wealth indicators, which is savings, assets, and income, as determining adoption in cluster 2, 3, and 4. And these are clusters which are more intensive and needs more investment. And then information access, especially to traders, is key for the yield enhancing clusters. I think that would also relate to the marketing aspect because these are farmers who are adopting that cluster. And then the tenure security, land topology, soil quality are key in adoption of clusters or all the clusters. And then livestock unit is also key for adoption of soil restoring clusters. So that is just a brief summary of the presentation in the table. And we use the traditional soil restoring cluster as the reference cluster. And then we have the cluster 1, 2, 3, and 4, just as I have defined them. And this is just, I have just explained this in a nutshell. And as we can see, the proportion of, out of the 3,837 plots, 1,397 plots are in cluster 3, which is the most adopted. And the least adopted cluster is cluster 2. So we also show the variances of random effect from the random effect multinomial logit. Here we have the within cluster variation. So we have cluster 1 up to cluster 4. Cluster 5 is the base, which is not included here. So the variation indicates the idiosyncratic individual effects within the clusters. And then we have the relative risk ratio, which is an exponential of the standard deviation of the coefficients. And as we can see from this, all the relative risk ratios are greater than 1. Now, for instance, if we take an example for the cluster 1, This implies that a one standard deviation change in random effect within that cluster would increase the probability of its adoption relative to cluster 5, which is the base cluster. And we also have the covariances of random terms from the random effect multinomial logit. So this shows the covariance between the various clusters, and the positive covariance, as seen here, suggests a similarity of degree of commonality in practices between all the clusters. And then we also see the correlation of random effect terms across all these clusters. So we can draw a number of conclusions from this. First of all, the estimations generally show adoption of clusters varies with time. They also vary with region and cropping systems. Secondly is that the key determinants include land tenure security, topology, soil quality, wealth, and access to social capital. And as we saw, households are with time disadopting cluster 1 and 5. And cluster 1 is basically what we would refer to as intensification cluster, and cluster 5 is basically the soil restoring clusters. And they are taking adopting more of cluster 2 and 4. So this is an indication that farmers are already acknowledging the benefit of SAI practices, because they are disadopting clusters that are more of only intensification or soil restoring, and adopting clusters that are a combination of both. And we also say that farmers are keen to get information on market prices. This implies the need to make economic gains from selling surpluses from their produce. And the results also suggest that directing policy exclusively on yield would be misguided, as this would require an holistic approach, as we can see that adoption of these practices depends on very many factors, including the socio-economic factors. So the main insight is that adoption of a suite of the SAI practices is context-specific, and there is no single cluster that would suit all farmers. So adoption of these clusters should be developed or packaged depending on different contexts as per region, cropping system, and social economic conditions. Thank you.